In a previous video, we discussed a search type called linear search, where we were able to look through an array and find an element, and we did so by just starting at the beginning and going all the way to the end, and if we found the thing, then we just said where it was or that it was in there, and if we didn't find it, then we said it wasn't in there. And so a searching process is when you look up a number, and then you either return that value, or you just say where it is, or you say that it's in the array in general. And now that we've done sorting, we can actually do something a little bit better than a linear search, and that would be called binary search. Binary search assumes that the array that you are looking through is already sorted in order. So here I've created an array, and it's already sorted from least to greatest. Now if I want to do a lookup, there's a kind of special way that I can do this that will be faster than doing a linear search. Now let me add one more element to the end of this. I think it would be nice to have an odd number of things. I have 6 right now. I think 7 would be nice. So let's add another one here. And so the idea behind binary search is very similar to how you might look up something if you were to have a page, let's just say, in a book, and you were to go look for it. Pages in a book are always in order, right? They just go from the smallest to the biggest, and if I told you to go to page 147, which is just kind of an oddly specific page and maybe like a 600-page book, then you might have an idea of where it is, but it's kind of hard to exactly guess that because it's such a big number, and you can't really count that out immediately. So what you might do is you might open the book to about the halfway point, right? So if I had a book that has 600 pages, you might open up the book, and let's say we're looking for page 147. You might open the book and just open it about halfway, maybe a little bit less than halfway, and you might end up somewhere where it's like 160 and 161, right? You don't open up directly to that page, but then you're like, okay, well, it's a few pages back, so you might open up the book a second time, right? So you might, open the left side of the book, and you might end up closer to 147. Maybe you end up at 142 this time, right? And so you keep kind of guessing with the part of the book that contains the page, right? So if I open it in the middle and I end up too far past it, you might try to look to the left of it. And so the idea with binary search is very similar to that. What we're going to do is kind of start at the middle, check if the thing we're looking for is there, and if it's not, we're going to look to the left of it if we know the thing we're looking for is less than what we want, and to the right of it if the thing we want is to the right of what we want. So here, let's start with an example. Let's say I look for the number 3, and I want to find out what position 3 is in. We know here, it's right here, it's in 1, but again, a computer can't really automatically know where everything is. It has to do some kind of lookup in order to find it. So what we do is we first consider what the length of our array is. Our length is 7, and so if we want to start at the middle, then the middle is going to be half of that. So here I'll put it down at the bottom. So the middle will be 7 divided by 2, and I mean integer division here. So that would be 3, right? So what we would do first is we would check, is the number 3 at position 3? So we look and we see, oh, that's 10. And so we don't find the number, but we know that the number we're looking for is less than the number that is in that position. What we can do then is we know that the number 3 cannot be over here. Definitely not to the right of 10, because 3 is less than 10. Knowing that, we can then check everything over here instead of checking everything to the right. So we've effectively cut the amount of things that we have to check in half. Now, this algorithm is going to work in a way where we want to keep repeating this half part, because if we do that, we can always take half of the remaining amount of the list, which will speed things up significantly. So even though this is only 3 things. If I had a list of 1,000,000 things and I split it down to half, I still have 500,000, which is quite a bit. So it becomes helpful to, even though you've pruned it down, to keep repeating this pattern and keep trying to take halves. So what we're going to do now is we know that it's over to the left of this, and so what we can do is we can simply check the thing that is going to be the middle of this list. So here we have this list now, right? And so we can simply take half of whatever the first half was. So the half here was 3. We'll take half of that. So the middle of the left half is going to be the previous 3 from up here, and then divided by 2. And what we're going to do is we're just going to go that far over. So in this case, that's a 1. So at that point, we know it's going to be 1 as far as the array to the left goes. Now this array starts at 0, so the position 1 is going to be here at 1. We're going to do a second example where we check the right hand side. It'll be a little bit different, but that means the next place that we check is going to be here. So we checked this one first. We said, okay, well, 3 is less than 10. We'll check the thing to the left of it, and we end up here, and we're going to check the first position because that's the middle of this array, right? The middle of this part that's to the left of 10 is 3, and then we check, is it correct? Is this the number that we're looking for? And it in fact is. So we found 3 in 2 steps. And if you notice, that would be the same amount if we were just to check from left to right. So in this case, the binary search isn't much better. But let's do an example really quick where it would be better. Let's say we have the same array again, but this time rather than check for something like 3, we want to see what position is the number 27 at. Where is 27 in the array? We write these out again. So 0, 1, 2, 3, 4, 5, and 6. And again, we say we always want to start at the middle and check that first. So here I'm going to check 10. I'm going to go here. It's the middle here because 7 divided by 2 is 3. And we see, is 10 equal to 27? And it's definitely not. And then our next question is 27 bigger or smaller than 10? And in this case, 27 is bigger than 10, which tells us that it's not in the left-hand side of this array. It's got to be in the right-hand side. And so, again, we've cut down the amount of searching we need to do into half. We can just look at the right-hand side, and we know for a fact that 27's got to be over there because this is sorted. And so, again, we're going to look at the middle of what's left. In this case, we're going to look at this array over here, this part, because we know that it's not 10 for sure, right? We said it's not equal to 10, so it's got to be in the thing to the right of 10. Right, so we're going to go to the middle of that. And in order to do that, we're going to find the middle of something that's length 3, which is going to be 1. Now this is a little bit different, whereas the other one, it told us the index directly, right? Because we were looking at the middle of the left-hand thing, it was 1. Here it's telling us that it's 1 to the left of the start of our array. And the start of our array is going to be 4, or the start of the array that we're looking through at least. So we look through position 3, and then we're going to look 1 to the left, or sorry, 1 to the right of position 4. And so the way we can find the list that's to the right of what we just checked is we know it's just 1 more than wherever the last place we checked. So the index we're going to check here is going to be 1 plus the last index we did. So let's say last index, and then we're going to add how far the middle is. And we'll do this in code in a moment. I'm just kind of spitballing it, but the idea is that, right, visually we want to make sure that we're in this right array, and then we know the middle is 1 because that's half of what's remaining, which is 3 elements here. And so we go here, then we end up at position 5, because the last index we started with was 3, right? The last one we tried was 3, that's where we checked the number 10. And then we add 1 to go to the right So we start here because that's the beginning of the list that's to the right of this, and then we add how far away the middle is, which is 1. And so we get that position 5 is the middle of the list that's to the right of where we just checked. Okay, and so we begin the process anew. We say, okay, well, we're at position 5. Is this going to contain the number 27, since that's what we're looking for? And we look at it and we say, nope, doesn't work again, because 27 is less than 30. But again, this helps us a little bit because it tells us that we are too far to the right of where we need to go. So the answer is to the left of where we need to go. Again, we'll calculate the middle. This list in this case, so all we have left of our list, because we now know that it can't be to the right of 30 because it's less than it. We've gotten rid of the 42, it can't be in that space. From an outsider's view, we can definitely see where it is. It's right there. It's the only space that's left. But here, what we would do is we would calculate the middle. How far away from the center is the middle? If we have a list of one thing, and again, this is integer division, so 1 divided by 2 is 0. And we tell ourselves, well, we want to use the last index that we did. In this case, we're going to start at basically how far over to the left it was. So we're going to look 1 to the left, and then we're going to add the middle, which is 0. Now I'm subtracting only 1 here, but you'll see when we actually implement it that this will just be the length of whatever's to the left of this. Right, so here this ends up being 5, since that was our last index that we used, minus 1, and plus 0, which is 4. So the next place we will check is 4 here. And so we check this position and we say, is this 27? And yes, it is. So 27 is at position 4. And there we go. We found it in 3 steps. So we checked 3 first, and then we see that it's not there, and then we checked 30 next, and then we checked 27 last. If you notice, this way uses 3 checks, but compared to the last one, which was the linear search, or sorry, the last method that we used, which was the linear search, that would have taken 5 steps because we would have had to check 0, 1, 2, 3, and 4. In this case, using the binary search is far smaller than using the linear search. And the bigger the array we get, you'll notice that the binary search does way better, especially if the element is towards the end of the list, if we use a binary search versus a linear search. So by cutting things in half every single time, we get a more consistently fast runtime. And that's why we would use something like this. Let's go ahead and try to translate all of what we just went over into code. Okay, we're over here so that we can do some programming. I've basically just copy and pasted our sorting code that we did in the previous video. Here I have the bubble sort, and then the 2 other functions that I wrote, the make random array and then the print array, and they're implemented down here. I've gone in Visual Studio and just made them shorter, but they do exist. Here in main, I'm going to create an array. It's going to be relatively big. It's going to be 1,000 elements. And then I'm going to randomly generate it. So I'm going to use that function I made earlier to randomly generate, and then I'm going to use the bubble sort that we made in the last video to sort it. After that, we're going to just randomly generate an index and then check if the element at that index, if we find it correctly, basically. Don't worry too much about my main code. Trust me, it will work. We're just going to focus on the binary search here. I've created a function called binary search, and all it's going to do is going to do the binary search that we just described, and then it's going to return the index of the element if we find it. Here we take 3 arguments. So the first argument is the array that we're going to be checking. The second element, or second argument rather, is going to be the length of that array, so we know when to stop. And then the third thing is the number that we're checking for, so the thing we actually want to find in the array. If we find it, we're going to return where it is, and if we don't find it, we'll just return I put 0, I think I mean -1, because 0 is definitely a possibility. So -1 would never be an index, right? So you'll find it's very common when writing functions to return something that wouldn't make sense just as a way to signal that it didn't work correctly. Okay, so the first thing I'm going to do is I am going to create a variable that represents the current index that we're going to be using, and I'm going to make that length divided by 2. And I think that's the only thing I really need to do. So this is going to be the index of where we're checking. Remember that the first thing we were going to check was going to be halfway into the array, and then after that we're going to kind of update it. Now I'm going to go ahead and keep searching while the length of the array that we're checking is greater than 0. So while we still have an array to check through, I'm just going to keep it at 0. And so what I'm going to do here, and it's totally valid when you do pass by value, which is what we're doing here, to modify this variable. So I'm going to just modify our length, and I'm going to split it in half every single time, since we said the amount that we need to check in the array is always going to get halved every single time we do a binary search. I'm just going to reuse this length variable and just divide it by 2 every single time. And so here at the very bottom, I will put the return -1 in advance. If we break out of the while loop and we have no array left to check, then that means that we didn't find it. So I'm going to put a return -1, and then we'll try to do what we said earlier and kind of update this. Now we have 3 cases. Remember, if we're checking an element, then we either found it or we didn't find it, which would lead to 2 other cases. It's either to the right or it's to the left. So first things first, let's do the equal part. So I'm going to say if array subcurrent index is equal to the number that we are wanting to find in this array, then that's great. I called it number to check. Let me change this to num to check just so it's shorter. In that case, great. We can return the current index since we're trying to return where we found it. That one's easy enough. If the place we're at is the one that contains the number, then return the place we're at. So that means that we're done. And so we're going to have 2 else cases here. So else if array subcurrent index is less than number to check, then we'll do some code, and then else. Normally I would just put else, but for the sake of readability, I'm going to put else if. You shouldn't actually do this if you're writing it, but I just want to make it more clear. Index is greater than num to check, and then we'll do something. So this second case here, if we kind of figure out what I just wrote here, it says if the current element is less than the number. Let me actually flip this around a little bit. I think it's just easier to read. Even though this is going to generate the same cases, I think it will be easier to read if I flip this really quick. And then we'll explain it in a little more detail. So if the number to check, the number that we are looking for, is less than the current number we're checking, then that means we need to check the number on the left, or the array on the left, the subarray on the left. So the number is smaller, must be on the left. And in this case, for the second one, if the number is bigger than what we're currently checking, then it must be to the right of it. Right, so now we can address looking to the left and looking to the right. So we need to update our current index in such a way that it moves it to the left or to the right. So here consider that when we go to the current index, if we want to find the starting point of the array to this, that's the left of this, then in the example we did, we were able to start at 0 and just kind of add to it. But that's not going to really work here because of the fact that we need to consider that what if we went right first and then to the left afterwards? Then the position that that array starts at might not be 0. And so what I'm going to do is simply move over. So current index, we're going to move over to the length of that array. And so the length of that array is going to be half of the length of our current array. Here I will maybe just update length. So we'll say length divide equals 2. So cut the length in half, since we need to make it half the size that it was going to be. And in that case, then this length represents the length of the array to the left of this one that we want to check. So if I take it and then go the length that that array is to the left, I'll end up at the beginning where it should be. So this will find, so far, the beginning of the array to the left of us, and then we need to add half of that on top of this. So we need to find the middle of that part, which would be the length divided by 2. And then that should work. So actually, I don't even need anything special here. I don't need any braces. I can actually just get away with one line. Right? It's kind of crazy to think that it really is just one line, and I'm not going to write too much, even though this is kind of a complex idea, right? And so the next one would be if it was to the right of it. And so in that case, we're going to need to find the current index, which is going to be what we're currently checking at, and then we're going to need to go to the right of it by 1. So we know that the beginning of the list that is to the right of the current element is always just 1 to the right of it. So this one's a little bit easier, whereas the other one we had to subtract by however long the length is to find the beginning. We just add 1 because it's directly to the right of it, and then we're going to add the length divided by 2. Now you might notice that it's probably a little more efficient if I just keep a variable that does this. Actually, probably not much more, but I'm just going to add half the length there. And now this should do it. I think that covers everything that we need to do for this. Yeah, that should be it. If we find the element, then that's great. We will return it because that's the element we found. Otherwise, we'll check the list to the left of it if it's smaller than it. So if it should be in the left list, then we're going to check the left list. If it's in the right list, then we will check the right list. Let's go ahead and run this and make sure it works. Okay, and I run it, and we see that we get the actual index is 667, and the found index is 667, so it seems to match. One thing I realized I forgot to do that would make this a little nicer, because it's always going to generate the same thing currently, is I should probably seed my random. One other thing I noticed when I was writing this, and I'm going to need to go back and correct this in the searching video, or sorry, the sorting video, is the fact that I put is swap in our sort, and that's correct now. I accidentally put not is swap when we were doing it last time. And so bubble sort actually was not working correctly. I accidentally made a mistake there, so I'm going to have to fix that. But anyways, let's run it again now that I'm seeding with a random, and we should see something other than 667, 202, and 202. 371, 371. So it seems to find it every single time. And if we were to compare this again to linear search versus binary search, you'll notice that it ends up being way smaller than if we were to actually do it with a linear search. In fact, if I have an array size of 1,000, the most it's ever going to take is 10 steps, which seems crazy, right? Whereas the other one, the most it will ever take is 1,000. If it has to go through the whole thing and find the last one, this one will actually find 10. 10 is the most amount of steps it ever has to take if it just halves it a bunch of times. And you can kind of tell that, right? If we divide this by 2 a bunch of times, you can divide 1,000 about 10 times before you hit 0 with integer division. And that's where I'm getting that number from, because we cut this into half every time. So this was just an overview of binary search. And in the next video, we're going to take a look at multidimensional arrays.